Hi guys, sorry for the technical difficulties. Okay, so here's our first question for A2 Pure Maths 3. We're going to start from the beginning. So again, the way to adapt these kind of questions is to force this thing to contain a factor of this, and then clean up your mess. So let's first, in fact, we can actually take 2x outside, might be the easiest thing, and then consider, sorry for the graphics tablet, it's being a little slow, x over x plus 2, which is the same thing. Now we're going to force this to be x plus 2 over x plus 2, and then we now have to subtract, we're missing, which was here we will get an extra factor of 2, so we've got to subtract 2 over x plus 2, which is going to be equal to, this is going to cancel, so this first thing will just become 1 times 2x, that's 2x, minus 4x over x plus 2. Again, this is not what we want. We want to attack this guy further, because the thing on the top is not just a linear, not just a scalar. We do exactly the same thing. We force this x to be x plus 2. And then we subtract off the extra thing we would get here, which would be over x plus 2, so that our factor, our quotient is what it's called, is 2x, and then here these would cancel, minus 4, and the remainder, 8. And that's all there is to these kind of questions. You just take each little power of x and you force it to be the denominator with, and then you do that until you get just a pure number over the factor. Okay, so question 2. This is a Taylor expansion question. So if you're familiar with, you should be familiar with the Taylor expansion for a variable around some value here. We're going to just expand it around 0, which is the Maclaurin series, technically speaking. So this is f of 0 plus f prime of 0, first derivative, evaluated at 0, times x, plus f prime prime, second derivative of f, evaluated at 0, x squared. And remember, there is a combinatorial factor of 2 factorial here. In fact, there is 1 factorial here, and there is 0 factorial here, but this is just equal to 1, and that's also equal to 1 for mysterious reasons that a number theorists can tell you more about. And this continues onwards. 1 over 3 factorial, f prime prime prime, evaluated at 0, x cubed, plus, and so on. So we have essentially our function in expanding, it's perfect as it is, it's an exact expression in powers of x. But this next bracket, which I'm going to express as 1 plus 2x to the power of minus 1/2, this thing needs some expanding in order to get into a nice power series. So let's call this function g of x, and it's the one we want to expand. So g of x evaluated at 0 is 1 plus 0, 1 over the square root of 0 is just 1. G prime, let's just differentiate first, is going to be equal to minus 1/2 times 1 plus 2x to the minus 3/2. If you evaluate it at 0, this just all becomes 1, so you get minus 1/2. G prime prime evaluated at 0, well, when you differentiate this again, the power of minus 3/2 is going to come down. So this is going to become minus 1/2, and then the bracket will again just end up as 1 times minus 3/2, which is 3/4. So, my bad entirely. When you differentiate, you should actually take this power of 2 out because of the chain rule. So, down with me, 2/2, so this is minus 1. Dumb mistake. Okay, and then again in here, that would just be minus 1. Oh dear, I don't know what that is. Minus 1 times 3/2 times 2 again, coming from inside. So this is actually 3/2. Okay, so they want us to have this whole thing up to including terms in x squared. So those will come either from this x term times the single x term in the expanded one, or from this linear term times the x squared term. Any higher powers of x are going to be overkill. So we only need to include up to this point and we're done. So now our f of x looks like 1 plus 3x times, here we go, 1 minus 1 times x plus 3/2, 1/2 factorial, which is just 2, x squared. So, oh God, I did the same mistake again. I forgot to cancel out that 2. So that's just a plus 3 over 2x. So let's expand this out. So we get 1 minus x plus 3/2 x squared plus 3x minus 3x squared. And this will give us 1 plus 2x minus 3/2 x squared. And that's all you need. So don't be silly like me. Remember to actually differentiate this properly using the chain rule. If you're at all in doubt, write them out like this before plugging them in. But as you get more experienced, you'll find you can do it on the fly. Okay, so question 3 is partial fraction decomposition. So this is a technique which is really useful in integrals. So imagine trying to integrate this, you'd wake up screaming. So the best way is to try and divide it into things which are a little more amenable to integration. Now, usually when you have partial fraction decomposition, you have something of this form, some numerator, function of x, over some denominator, function of x. And this can only be done if the degree, which means the highest power of x, of n of x, is less than the degree of d of x. This is the only time this procedure will work. Backwards, this normal procedure of pulling fractions together into a common denominator. You have to be a little bit careful. So you will now express this as a sum of terms each one over some factor of the denominator. So here we have x, and we have x squared plus 1. If I gave you x, if it was x squared minus 1, maybe you could further decompose that into x plus 1, x minus 1, in which case you'd use each of these individually. But here we can't divide this while staying over the real numbers. That would require imaginary numbers, so we keep them as these two. Now, our function is now going to equal something over x, no problem. And then it's going to equal something over x squared plus 1. Now, this thing needs to include all possible terms in the denominator that we've chosen. So here, no problem. This thing is degree 0. We're assuming that these a's and the b's and c's that I'll write are real numbers, not factors of x. And this is degree 1. Is degree 2. So we need to represent a general equation of degree 1, so it's strictly less, by which I mean bx plus c. That is what we need, because this whole thing is now degree 1. 1 is the highest power of x. We need for this question. Now together, and you'll get a plus 1 plus x times bx plus c all over this business, and you just equate the denominators. That's all there is to it. Okay. 4. Right, so this is just testing that you know what an value symbol is, or a modulus symbol. Now, this notation is exactly the same as that is used in complex numbers, but in this case, we're assuming we're just over the real, so it means, this just means take the positive of either side. No problem. So there's two ways of doing this. Either you can sort of write out the logic explicitly. So if the absolute value of 4x minus 1 is equal to the absolute value of x minus 3, then 4x minus 1 must be equal to either plus or minus x minus 3. And this then you can split into two equations and get the answer. Or you can just square both sides, because the square of the reals is always positive. So you can actually once you square it, you can throw away the absolute value signs and just say 4x minus 1 all squared is equal to x minus 3 squared. Multiply everything out, quadratic solution. Both of these are equally valid. And like at the quadratic, you'll get two answers for x, which are the same as the two answers you would get from each of these solutions. So in part 2, they're asking you to be able to recognize that this is the same thing as 4 times 4 to the y, and that therefore this equation is the same as that one with x is equal to 4 to the y. And then you will get, you'll compare your answers. So let's say we got a and b, some numbers for x, and you will go there. So x, which is equal to a, is equal to 4 to the y. What is y? Well, y must be equal to log base 4 of a. And if you want to make this nice to your calculator, it's just the log of a over the log of 4 in any base. So natural, e or 10, whatever your calculator, whatever you're used to. And that's just by the rules of logarithms. Now, there's a little bit of a subtlety here. One of the answers that we got in question 1 is negative. So one of the answers was actually minus 2/3. So we were faced with the possibility of having an equation of 4 to the y is equal to minus 2/3. And they require you to notice that no power of 4 will give you a negative number. There is nothing I can raise 4 to. If I raise 4 to a positive number, I just get a number greater than 4, you know. Sorry, greater than 0. So even if that's fractional, even if it was 1/2, well, that's just the square root of 4, which is not negative. The cube root of 4, the 19th root of 4 to the power of 6, all of these things are positive. So no positive number up there would give you something that was negative, nor would a negative number, because a negative number, 4 to the minus a, is just equal to 1 over 4 to the a, and we've just established that 4 to the a will always be positive, so 1 over will still be positive. So this thing is just not a solution, and you have to tuck it away. So you'll reach a single solution, and you'll find that with the calculator via this, and make sure you get to 3 significant figures. Okay, so this question basically is, the first part is just testing your understanding of the product rule or the quotient rule. Either is fine. So you may have memorized the quotient rule explicitly, that say d dx of f of x over g of x is equal to f prime of x times g of x minus f of x g prime of x all over g of x squared. Now this just comes from the product rule. So you only have to remember the product rule, which is that dx of f of x, it's called h of x, is equal to f prime h plus f h prime. And you see how that is exactly the same as that if h is equal to 1 over g. Because in that case, h prime is going to be equal to minus, because there's basically g to the minus 1, minus 1 times g prime all over g squared. So all that does is this h prime will go into here, and then you'll pull this guy over this g squared. So this thing is h, which is 1 over g. And then you'll pull it over 1 over g squared, which will give you a g over here, and it's exactly the same rule. So if you're going to remember one of them, remember the product rule. Okay, so to the question. Here we've got, I think of it as 2 functions, multiply together, 1 plus x squared, 1 plus e to the 2x. And they're asking you to differentiate them. You get, minus 1 there, so minus 1. So you differentiate this, no problem. You differentiate this. Honestly. So of the whole thing, minus 2 e to the 2x all over 1 plus e to the 2x squared. You follow the product rule and you get your answers. Then you must recognize that when the curve crosses the y-axis, I mean, this is trivial to recognize, x is equal to 0. So you set x to 0 there, and you find dy dx. Next question. Well, This is pretty much exactly the same procedure, except it's not given in the form of y is equal to something, but that is not going to stop us. What we're going to do is just apply d dx as an operator, as an operation, to the entire thing. So if we have 2x cubed plus 5xy plus y cubed is equal to d dx of 0, which is 0, and we're just going to be really religious about using the chain rule. So d dx of 2x cubed, well, that's just, oh my goodness, 6x squared, no problem. Now we're going to apply d dx to this thing. Well, it's going to be product rule, first of all, because we have 5x times y. So d dx of 5x, well, that's just 5. So our first term is 5y. But now we're going to move it through, product rule, remember. So this is, remember, f, and this is h. So f prime was 5. F prime times h is 5y. Now we need the second term. So what's g prime? Oops, h prime in this notation. H prime, well, that is just y differentiated with respect to x, right? It's y prime, which is equal to dy dx. And then we just don't know what dy dx is. That's actually what we're trying to find out. So we just leave it as dy dx. Term is f, which was 5x, times dy dx. Now this third term, y cubed. Well, again, we use the chain rule. So our function, let's call it g, is equal to y cubed. Well, what's dg dx? It's going to be chain rule, dg dy dy dx. Well, dg dy is just going to be 3y squared. Dy dx, we leave it alone, that's our third term. Plus 3y squared dy dx. And this is sometimes called implicit differentiation. But basically, you just hit everything with that operator, and you follow the chain rule and the product rule mercilessly, and you will get your answer. So here again, we set x equal to 0. And we solve for dy dx. And the other thing to notice is that when x is equal to 0, y is equal to, well, we go back to the original equation, and we notice that it's going to be the cube root of 8, which is 2. So because that would go, which would be y cubed equals 8. So now we know everything in this equation, except for dy dx. So we have 5 times y, which is 10, plus 3 times 4, which is 12, dy dx is equal to 0. So dy dx is equal to minus 5/6. So that was our procedure here. Differentiate with respect to x, plug in what values we know, and get the answer. This implicit differentiation, once you've done it a few times, you really, you'll just be applying the chain rule all over the place. It's all following the rules. There's nothing actually new here. Okay, so this is a vector question, obviously. We have two vectors, P and Q. I'm just going to draw a schematic here. I'm not going to try and draw them in 3D, or they're, genuine positions relative to each other. P and Q, we have some line between them, and we have some midpoint A. Let's say our origin is, I don't know, over here. So they're asking us to find a plane, the equation of a plane which passes through A and that is perpendicular to this line PQ. So something like with a right angle there. Well, as soon as we see the word perpendicular, we know a dot product is going to be involved in here somewhere. But let's do some bookwork first. First, let's find out a vector for the line PQ to actually tell us the direction. So we have P, we have Q. So the vector P to Q is minus OQ. Wait. Yes, plus OP. Actually, this is the line QP. I got a bit mixed up. I must get the directionality right. Okay, QP is minus OQ plus OP, because if you want to get from from Q to P, you need to go back along the vector from, so the normal vector OQ goes like that, and you go backwards, so it's negative, and then positive along to get to P. That's how you get from Q to P, minus OQ plus OP, which in this case is equal to 12, 6 minus 6 in this vector notation. Next, we need to find A. Well, A is the mid point on this line. So if you want to get there, all you need to go is either you go to Q and then go halfway up this line, or you go to P and then go sort of minus halfway down that line. That'll get you to A. So let's take the first way, and we say that vector A, I'm mixing notations terribly, but people do that all the time. It'd be good to get used to it, is OQ plus 1/2 QP. We're only going halfway. And this will give us the vector 1, 4, minus 2. So this is what I would call the vector A, but actually it should more strictly be OA, is the same thing. So we have this plane. Now a plane is just an infinite number of points, in the same way that a line is an infinite number of points, but they span like a two-dimensional space. To get to somewhere on the plane, what you need to do is go to A first. Once you've arrived at A, head out in a direction that's perpendicular to QP. So let's express that. So pi is my point that's on the plane, because the plane is called big pi, is first go to A, and then go along some vector V, where V dot QP is equal to 0, i.e. they're perpendicular, the dot product vanishes. Now, we want to find this V. We don't know what it is yet, but what we know, well, we can rearrange this. We can say that V is equal to pi minus A, and we know that pi minus A, that V is perpendicular to QP, therefore pi minus A is perpendicular to QP. So we can express that as, well, pi minus A, let's just say that pi has coordinates x, y, z. So x minus ax, y minus ay, z minus az, dotted with 12, 6 minus 6 is equal to 0, right? So we can, this is just a simple substitution and solving. So we know that that's 1, that's 4, and that's minus 2. And you take your dot product, 12 times x minus 1 plus 6 y minus 4 minus 6 z plus 2 is equal to 0, and you'll get something, and then you just expand it out and you get something in that form. Now they're talking about another line, which is parallel to the x-axis and meets pi at the point B. So let's think about the equation of this line. We know that it hits the point B and that it's parallel to the x-axis. So we also note it also hits the point P. So our equation for this line L, let's go to B, or rather let's go to P, because we know P. So OP, and then we go, this is just a parameter, lambda, we go some amount in the x direction, i.e. parallel to the x-axis. We get to P, and then we travel up and down. So if this is P, if this is O, and this is the x-axis, that means that any point of the line can be reached by going first up to P, and then along, and there is your point. So these are all the points that form the line. Just because this sort of vector crosses the x-axis, that doesn't matter. The point is to get to the line, you have to first go to P, and then lambda sort of parameterizes how far you travel. Do you go here, or minus, go backwards, and so on. So we're also told that the line passes through B. So let's say point B, which is on the line, is equal to OP plus lambda B 1, 0, 0. So this is a specific number now that will get us to B. We always go OP and then we go somewhere. And this happens to be the place where it meets the surface pi. Well, in that case, it must satisfy pi's equation. So all you have to do is plug the x values. So here the x values are going to be whatever OP was, 7 plus lambda b, 7 minus 5. So that's what b is. We don't know what lambda b is yet. And we know that this satisfies the equation that we got for pi. Plug in each of the values. The only unknown is lambda b. Solve for lambda b. So we get lambda b is equal to minus 9. And that gives us the vector b. Now they're asking for the distance AB. So there's, a straight off formula to do this, or you can think of it as finding the vector from A to B and then taking the magnitude, which is how I prefer to think of it. So the vector from A to B, if you want to get from A to B, you go backwards from A to the origin, and then from the origin to B, because this is also OB. So it's going to be minus A, AB, minus A plus B, which will give you minus 3, minus 3, 3, minus 3. If you just add them together. If you take the magnitude, and again, this notation with the modular signs, in this case, it means taking the length of a vector. Well, that's just by Pythagoras, the square root of 3 times 3 squared, 3 copies of it, which is 5.20 to 3 significant figures. Okay, so that was, a question that required you to get a feel for a lot of things about vectors. But draw a diagram if you have time, and think about vectors as sort of taking you from one place to another. Okay, so the next question is complex numbers. Most of these can be solved just by, and I know you may feel that you don't have to, you're really comfortable with complex numbers, but if you're in any doubt whatsoever, rule number 1, substitute in terms of real numbers. So W is a complex number, and I'm going to say that it's equal to X plus IY, where x and y are real numbers. This just makes everything easier to get on with. So without a calculator, not that a calculator would help, we solve this. So we go 3 and just x plus iy plus 2i, and the complex conjugate, well, that's just x minus iy, which is equal to 17 plus 8i. And now this is just an elimination problem. Just remember that I squared is equal to minus 1. And then remember that you can equate imaginary and real parts. So if I have x plus iy is equal to a plus ib, then that means absolutely that x is equal to a and y is equal to b. The real and imaginary parts are completely independent. So you cannot have this any other way. So, yeah, you have this equation, which gives you for which you have two unknowns, x and y, right? And it may look like just one equation, but it's actually two, because you can equate the real to the real and the imaginary to imaginary. That gives you two equations involving x and y, and therefore you can solve it. So we get, just you want to check your work, 7 minus 2i. Right, so the second part is a little more difficult. It's more to do with thinking about these imaginary numbers in the complex plane. So the Argand diagram, you may recall, is the one with the real axis and the imaginary axis. And any complex number can be represented as a point. So the imaginary part gets mapped onto the y-axis and the real part to the real axis. So they've given you these two facts about this imaginary number z, talking about the argument and the modulus. So these are very intertwined with collaborative of complex numbers, that any complex number z can be represented like this. Now, the proof of this is quite beautiful. It involves something called Euler's formula, which is that ECI theta is equal to cosine theta plus I sine theta, or de Moivre's. And so this sort of gives the real coordinate, i.e. the x coordinate, the real part, and this the imaginary part. And this thing is then r cosine theta plus I r sine theta. Now if you think of, let's get rid of this specimen here. If you think of our point in the plane, you can think of the x coordinate here and the y coordinate on the other side. You can also think of it as having some magnitude r and some angle theta. So what is this distance? Well, it's just r cosine theta. And what is this distance? It's r sine theta. And that is the x coordinate and the y coordinate, the x coordinate and the y coordinate of this point, in exactly the same way as 2 plus 3i is a coordinate. So this theta is called the argument, and this r is called the modulus, because in fact r is equal to the mod of z, mod being the length, as you can imagine, which is square root of the real part squared plus the imaginary part squared. And that's just by Pythagoras. You can think of it in the Argand plane. Right, to the question. They're telling us two facts. So let's look at fact number one, or A, that the arg of z, not z, but z minus 2i is equal to pi over 6. Well, a formula for finding the argument over here. Think about r cosine theta is x, and r sine theta is y. So y over x is equal to sine theta over cosine theta, which is tan theta. So if you've got the y and x and you want to find out the argument, theta is just equal to the arctan of y over x. And that is the arg. So what they're saying is that the argument of this complex number is equal to pi over 6. Well, again, just make z into x plus iy. So the argument of x plus I y minus 2, so I'm putting them together, is pi over 6. So they're saying that the argument of this composite, that this complex number, including the 2, this new complex, it's a point somewhere else, it's not where z is pi over 6. So that must be equal to the y value, which is the imaginary value, y minus 2, divided by the x. So this is true. So we know that y is equal to, oops. The arctangent, mustn't forget that, y minus 2 over x. So therefore, y minus 2 over x is equal to the tangent of pi over 6, which you may remember from your specimen triangles. That's pi over 6, the small one. That's 1, 2, square root 3. So the tangent is going to be 1 over square root 3. So this means our first equation is y is equal to 1 over the square root 3x plus 2. So that's, we're asked for the place where these two lines intersect. So the first line is defined by this equation, equivalent to this equation in the argand plane. The second line is defined by z minus 3 is equal to mod of z minus 3 is equal to the mod I. So here mod takes on a different meaning. The mod plus iy is equal to the square root of x squared plus y squared. It's the same thing as saying the square root of x plus iy, x minus iy, z star square rooted. That is the mod of z. So basically it takes a real number, it takes a complex number and it gives you out a real number. If you take the complex modulus, if you just took the square, you'd end up with still a complex number. Try it for yourself. But if you use the modulus, that's not the square, you've taken the complex conjugate here, and that turns the whole thing real. So they're saying that the modulus, the length of this, is the same as the length of that. So why don't we just express this again as x plus iy minus 3 is equal to x plus iy minus 3i. And I'm just going to express it a little more suggestively, x minus 3 plus iy is equal to the mod of x plus iy minus 3. And now we're basically good to go. They're telling us the modulus of these two are the same. So the square root, or in fact, let's just square both sides. So that x minus 3 all squared plus y squared is equal to x squared plus y minus 3 all squared. Easily solve, and we end up actually with y is equal to x. And then we're all asked to find the place where this and this coincide. And they want us to express this in polar coordinates, which is what these things are. This r e to the I theta. Well, we know that this line, y is equal to x, well, that's just going straight through like that, right? We know what the angle of that is. It's going to be 45 degrees, or pi over 4. And if that's what the angle of the whole line is, it's going to be the angle obeyed by a point, any point on the line. So therefore, by this point, intersection point P, where P meets this other, the first one we looked at, which goes like that, maybe a bit steeper than that, like that, something. So we know that pi over 4 is the angle. And now we want the distance from a center. Well, we can just solve the equation to find where they meet. We find the x-coordinate, we find the y-coordinate, and the modulus r is just the square root of x squared plus y squared. So remember, if you find x, you know what y is because they also obey this equation where y is equal to x. And that's all. So that was a little trickier. Right. So this is talking about integration by parts. So that's the one, it's in your formula booklet, but it's the one schematically, which is that f g prime is equal to fg minus the integral of f prime g. But it's written in Leibniz notation in your formula booklet. But let's look at the integral, I'm just going to forget the limits for now, of 4x of x dx. Well, the thing we would like to, we always look at with these partial differential equations, what would we like to differentiate? And in this case, sorry, differentiate here. And what do we kind of want to avoid integrating? Well, I kind of want to avoid integrating the natural log of x, okay? So here, I don't have to integrate f, I only have to differentiate it, so I'm going to call that f, and I'll call that g. I'm much happier integrating 4x than integrating natural log of x. So f, remember, even though I'm not writing, let me write the limits, 2 to 4. Don't forget that this is a definite integral, so anything that sort of comes out here must also be between those two limits. So it's going to be f, which is the natural log of x, times the integral, sorry, this is g prime, my bad, the integral of 4x, which is going to be 2x squared, and that's evaluated between 2 and 4, minus the integral of this integrated, which was 2x squared, times natural log of x differentiated, 1 over x dx. Okay, so let's look at this guy. So this is going to be 2 times 16, 32, natural log of 4, 4 times 2, 8 of 2, minus, well, this x cancels with that power, minus 2, integral of x is 1/2 x squared, evaluated between 2 and 4. Okay, so this first business, rules of logarithms. Let's first make this 4 into a power of 2. This is just 2 squared. Logarithms, log 8b is equal to, so that can come out, times 2, this becomes 64. 64 minus 8 is 56. Natural log of 2 minus 4, 4 squared, 16, minus 2 squared, which is 4, minus 60, minus 12, which is the answer required. Come on. There you go. Second one, this integration by substitution. So I'm just going to put this stuff back up here. Now, integration by substitution can go very badly wrong. You can end up writing 3 pages and get back exactly what you started with. The trick here is to, be able to sense a pattern in what is going to simplify life for you. I'd say first substitute in for dx, and then look what next to do. So we have that u is equal to, oh, excuse me 1 second.
Okay.
So here they've given us a substitution, which is u is equal to the sine of 4x. So firstly, we must adjust for our measure of integration. And we get that du dx is equal to 4 cosine 4x. So we can immediately rewrite our integral. And we can say, it's probably the nicest integration sign I've ever written. We can say that this integral is now, we're going to leave the stuff inside alone, cosine cubed of 4x. Dx, so dx is now going to be equal to du over 4 cosine 4x. That's what I mean by replacing the measure. This thing is called the measure. It basically tells you like how you're going to integrate over stuff, like what does it mean to be a little line element, little infinitesimal piece. It's the measure. Well, now we notice that we can cancel one of those, and then we can use the trig identity to express this. Oh my goodness, what's going on there? We can express this as the square root of 1 minus sine squared of 4x du. Well, isn't that just 1 over 4, square root of 1, sorry, should not have been the square root because it was cosine squared. Oops, that actually would have been horrific. Just 1 minus sine squared. And that means we've got 1 minus u squared du, super easy integral. So it's 1 over 4 times u minus 1/3 u cubed. Now there's 2 ways to do this. Either you can substitute back in x and evaluate it in the original limits, or you can translate the limits to u. So since u is equal to sine of 4x, when x is equal to pi over 24, then so this is the, x is equal to pi on 24, then u is equal to the sine of pi over 6, right? 12, yes. And this, again, we look at our guy, 1, 2, well, that's just going to be a half. And when x is equal to 0, u is equal to 0, sine of 0 is 0. So our limits for u are 0 and 1/2. So that's going to be equal to 1/4, 1/2 minus 1/3 times 1 over 2 cubed. And that is equal to 11 over 96. So here, I would recommend immediately plugging in this for dx, getting in terms of du, and seeing things cancel, and then a solution will spring to mind. If you had tried to substitute in here, you may have actually led yourself down the garden path and sort of taken ages to get there. And time is precious on the exam. Right. So this question is just asking you to apply the trig identities, which are given, especially the double angle identities, which are given in the handbook. So we're going to say that, So there's several ways to do this, but I think the easiest is just to say that 4 cosine theta plus 3 sine theta is equal to r cosine of theta minus alpha, and then just find what r and alpha are. Well, first let's use the identity for when you're adding angles together. So this is going to be equal to r cosine theta cosine alpha plus sine theta sine alpha. Right, so you can picture, the key fact to remember is that cosine and sine terms are added independently. And what does this mean? I mean, it means that like the imaginary and real parts above, you can equate cosine terms and sine terms. Now this is to do with the way that you add frequencies of different waves to build a third wave. One moment.
Can I just check, because it looked like it stopped streaming? No? Seems to be going on. Okay. Brilliant. Apologies. It looked like it stopped streaming, but it seems to. Yeah. No worries.
Cool. I hope everyone can see this. Just Tom was saying maybe it might have stopped streaming, so let us know. Okay, so we're talking about adding, so each of these is a wave, you know, cosine and sine. Sine, you've got all these different possible waves, could be different arrangements of sine waves. You've also got, you know, all your cosine waves, and maybe you push them along and they look like sine waves. But the way you add frequencies together, especially if you think of, you know, the waves that are made in electronic equipment, maybe this is actually made of loads of subwaves that sort of add together. Oh my goodness. Okay, this is not the graphic style for this. But the point is that you can equate these, and we can think of these as coefficients. 4 is a coefficient of cosine theta here, and the coefficient of cosine theta here is r cosine alpha. Same deal, 3 r sine alpha. So we've equated the coefficients on either side. So once you've done that, and you realize that r cosine alpha is equal to 4, and r sine alpha is equal to 3, you can easily obtain, so you can either go that r squared is equal to 4 squared plus 1. Wait, that's not right. Wait, why did I write 1 then? Sorry. 3. 4 squared plus 3 squared, which means that r is equal to 5. Or you can divide these two and go that sine alpha over cosine alpha, which is equal to tan alpha, is equal to 3/4, and then take the inverse tan, and this will get you alpha. So that is all that's required, and now they're asking you in the second part to solve the equation that this business, equivalently this, is equal to 2. So you have r is 5, so you have 5 cosine theta minus alpha is equal to 2. And by the way, I'll give you a value for alpha here. Let's just so we for concreteness, 0.64 radians. So this is obviously going to is equal to the inverse cosine of 2 over 5 plus alpha. Now this is going to give you your principal value of theta, no problem. But the point is that they're saying theta can be between 0 and 2 pi, so they're going to be more than one value. Because remember, these things are periodic. There is a subtlety here. Usually, you'll get something of the form cosine theta is equal to blah, and then theta is equal to inverse cosine of just some blah with no alpha here, and therefore theta is principal value that, and then you subtract 180 minus that, and no. But that's because here you have theta equal to, or the cosine theta being periodic, and the theta be equal to a single item here, like just a single term, which is this inverse of a periodic function. Whereas here you have this alpha on the end, so let's be a bit careful. So principal value of theta is going to be 1.78 radians. Now the thing that is periodic is the cosine of theta. So really, this actually might be better done by considering the various values of theta minus alpha. These are going to be several. So you see here that for the cosine function, two fifths, the value at like 2/5, which is about here, happens there, it happens there. If you go negative, it happens there. And you're going to find two values of theta minus alpha, basically. It's going to be this one and this one. Essentially, you have to reevaluate the limits that you're allowed. So when theta is equal to 0, this is equal to minus alpha. So theta minus alpha must be greater than minus alpha and less than 2 pi minus alpha. But alpha was only 0.64 radians, so it doesn't actually get you there or take off that one. So it really is just these two. And so you consider this value and also 2 pi minus that value. And then you use those as your two values of theta minus alpha. And therefore theta is equal to this minus alpha minus alpha. So that's just a little weirdness. So if you see this kind of construction rather than the straightforward one, be careful that it's this thing that's periodic, not this theta itself. So now they're asking us to integrate the this thing that we found. And so let's say our integral, it's the integral of 50 over, and I'm already going to substitute it in, 25 cosine squared of theta minus alpha, d theta. Now I'm going to use a little substitution just to make my life a little easier, where x is equal to theta minus alpha. And you'll notice that this leaves the measure unchanged. dx is still equal to d theta, because alpha is just a constant number. So my integral I is equal to integral, oh my goodness, integral of 2 over cosine squared x dx. Well, that looks a lot more tractable. Well, what is 1 over cosine squared x? Integral 2 sec squared x dx. And it. And now we're going to substitute back in for x. So it's going to be 2 tan of theta minus alpha, and then evaluate between the two limits. Did they give us limits? No, they didn't. Okay, it's 2 tan theta minus alpha plus a constant, because we don't have limits. Okay, so this is the last question. And it's a differential equations question, but luckily nothing too strenuous. It's going to be separation of variables. There's not going to be any, auxiliary equations or any funky stuff like that. So what are they giving us? Well, they're giving us that there's an empty tank, and the volume at some point is V of t. And they're saying that the inflow, the increase per minute is 80 centimeter cubed, and the loss per minute is kV centimeter cubed. So the loss depends on the actual volume that's there. So let's say the rate, let's build our differential equation. The rate of change, dv dt, v is a function of t, is equal to 80, that's just constant inflow, minus kV. Well, this is a very boring, inhomogeneous, sort of first order ODE. And basically the idea is you separate variables. You want anything that has V involved over here, and sort of multiplying or dividing the dV, not added to it. So we can't just take the kV over, we have to take this whole thing over. So we get that dV over 80 minus kV is equal to, and then we take the t over there. Now we want to integrate. So we integrate both sides and think about our limits. We want to talk about between time 0 and time t. Now, because I want to talk in general, I'm talking about some time in the future t, but then it can't have the same name as my integration variable. Integration variable, the name does not matter. We're just using, t here, but I'm just going to call it t prime to make sure that this is a definite time of t, even though I don't know what the time is. This is a dummy variable, an integration variable. Same with v here. I know that at time 0, the limits have to match. At time 0, the volume is 0. At time t, the volume is v. So I have my limits all sorted out. Right, so what's the integral of this? Well, you should know that from integration that it's going to be that if our function is 80 minus kV, then df dv is going to be it's going to be minus k. And here we've basically got that situation. We're just going to have an extra factor of minus 1 over k. Sorry, by that situation, I mean the situation where you've got df dx over f dx is equal to the natural log of f of x. So here we have the natural log of 80 minus kv. But if we differentiated this, we would get an extra factor of minus k coming out. So this has got to be minus 1 over k to compensate that. And remember, I'm still integrating. So this is between 0 and v is equal to, well, this is just the integral of 1, so it's just t. Valuated between t and 0 is just t. Well, this thing is going to be minus 1 over k. Evaluated at v first, natural log of 80 minus kv. Don't forget the 0, minus the natural log of 80 minus 0, natural log of 80. We might be tempted when we have a 0 down here just to throw away the second subtracted term, the lower limit, but obviously that can be foolish. So that means that the natural log, rule of logs, 80 minus kv over 80 is equal to minus kt. Therefore, 80 minus kv is equal to 80 e to the minus kt. And you can see where that comes from. So now we have our expression for v by solving the differential equation. Now we are asked to use an iterative formula. So this is just extremely mechanical. You're given a formula, right? Unfortunately, you want to solve for k, but you have k both in there and over here. It's really hard to find out what it is in any absolute terms. In fact, it probably isn't possible to actually do it analytically or exactly. So you have to use numerical methods, which are these iteration methods, which usually you would do in a computer. But they're asking you to do it by hand. So what you do is you start off with your k0, Then you plug it in to the formula, this one, and you get a new value of k, k1. Equals whatever. This then goes into the formula and gives you k2. Repeat, repeat. Now you stop when you've got the required amount of precision. You know that something is getting more accurate if successive iterations aren't really changing it very much. So if I had like something, I don't know, 2.1359, and then, so they say here, show each iteration to 4 significant figures, but you want 2 significant figures of accuracy. So if my next one was 2.1493, well, 2 significant figures, those have changed in this last iteration, so I don't think it's precise enough. I don't trust either of these. When I plug that in, maybe I get 2.1482. Well, that's looking good. This hasn't changed. I did one more to be sure, 2.1481. Well, no, I definitely trust this because it's not changing very much. So, last sub-question. They want you to determine how much liquid there is in the tank 20 minutes after the liquid started flowing. Well, super easy. Just substitute into this equation. Don't need to tell you how. And then they want to know essentially the long-term behavior of the liquid in the tank. So this function v, it's some number at the front, who cares? 1 minus e to the minus kt. Well, this sort of function will in the future look familiar. It's a function where you start at 0, so we can just look. 0 is going to be 80 times 1 minus e to the 0, which is 1, which is 0. And then it increases, but it increases to, well, the amount by which it increases is kind of dependent on this number here, and it gets less because of this negative sign and the fact that you're subtracting from 1. So you have this maximum amount that it can reach, and it can't really get higher than that. Think of as t goes to infinity. So v, as t goes to infinity, well, see, this is why I'm being confused the last 2 minutes. This is supposed to have a 1 over k. So it's actually a little bit bigger. But because k it turns out to be less than 1. So this thing's a bit bigger than 80. But let's call that v max. And I'll show you why. As t goes to infinity, this thing goes to minus infinity. So it's 80 over k, 1 minus, remember the minus just means it's on the bottom, so it's 1 over e to the minus kt. Well, if this is going, plus 1 over e to the kt is e to the minus kt, sorry. So it's 1 over infinity just becomes, basically, the limit is 0. So this is just equal to 80 over k, which is the highest that this can be, because 80 over k times 1 is over here. Everything else at any other point is subtracting from that. So let me stop being so mysterious and just show you the diagram. You start at 0. This is b. This is t. At some point, there is our v max. And we do this. And you might recognize this from is sort of the fact that it's 1 minus e to the, it's about 1 minus e to the minus t. That's sort of behavior that we're expecting of the function. And e to the minus t, it's an exponential decay function. It's like this. So really, it's kind of like this has been, whatever this is, is being subtracted as time goes on from the function. And that's the end of the paper. Thanks for listening.